In the last lecture of this section 3.1, we look at the terms humidity, evaporation, and boiling. So vapor pressure actually was mentioned in an earlier section. We'll come back to that here. The pressure at which a gas coexists with its solid or liquid phase. So vapor pressure is sort of the natural balancing point where the evaporation of the liquid is matched by the condensation of the vapor onto that liquid. So an example would be, imagine you had a bottle of water and there was an opening above that bottle where air could exist, but then you pulled all the air out, you create a vacuum. Well, that area above the water would have zero pressure. So if you had some container, sealed container, where the bottom was filled with water, and you just had a vacuum on the top, what would happen is that water molecules, because they're traveling at some speed, right, there's kinetic energy associated with it, would break away and start to deposit water vapor in the atmosphere or in the area above the liquid water. Now the entire amount of liquid water won't disappear, but you'll get some water vapor above it. Now that water vapor, how much water vapor depends on the gas that we're talking about, or the element that we're talking about. If we're doing this in liquid nitrogen or carbon dioxide or liquid oxygen or whatever. Again, water is something that we can use because it usually occurs at higher temperature. So eventually some of these water vapor molecules will actually condense back into the liquid. So it's a constant cycle that a couple of atoms or molecules of the water will evaporate, right, become a vapor in the air, but then some of those vapor molecules will actually deposit or condense down into the liquid. And at the pressure at which that balancing act occurs, where at low pressure you'll get more liquid turning into a gas, at high pressure you get more gas turning into a liquid, but the balancing act of where an equal amount of gas becomes liquid and liquid becomes gas, the process balances. We call that the vapor pressure. And you can see that a little bit if you think about soda or any carbonated beverage, right? If you crack open a 2 liter of Coke or Pepsi or whatever you drink, you hear the hissing of the gas that's escaping. Well, that means that there was an additional pressure built up in that 2 liter. Well, why? Well, it's the pressure built up from the carbon dioxide dissolved in the liquid. Carbon dioxide is trying to escape, trying to bubble out, right? So if you, undoubtedly, we've all experienced this, right? You open up the cap of a soda and you leave it off, eventually all the carbon dioxide will escape. At atmospheric pressure, the carbon dioxide, most of it doesn't want to stay dissolved in that liquid. But if you cap the 2 liter, after you put your fresh soda, so you have a soda stream that adds carbon dioxide, after you create your new soda, fully carbonated soda, and you cap it, that carbon dioxide is still trying to escape the liquid, but pressure builds up inside that 2 liter bottle or whatever bottle you're using until the pressure gets high enough that the amount of carbon dioxide that is escaping from the liquid balances the amount of carbon dioxide in the air that's being dissolved into the liquid, that's being reabsorbed or condensed into the liquid. So you have that balancing act. And clearly the vapor pressure for carbon dioxide is higher than atmospheric pressure. That's why you get that hiss of released gases when you open that 2 liter up. Another term we can talk about, relative humidity. Now, your book talks about the old expression, right? It's not the heat, it's the humidity. And in reality, that's quite true, right? Our body temperature is normally 98.6. We feel comfortable usually when we're wearing, a layer of clothing in a room that's 70 degrees Fahrenheit. Well, why? Well, our body naturally produces heat energy as part of the chemical processes that run our muscles and our brain and our liver and all of our organs. And that energy has to escape. That energy escapes usually through the process of heat conduction. We'll talk about that later on in this section. heat conduction or evaporation. So you sweat, right? You produce sweat. As that sweat evaporates, it takes with it that excess heat energy. If there's very little water vapor in the air, if the humidity is low, then it's very easy for sweat to leave. In fact, you can have dry skin. If the humidity is high, that means there's a lot of water vapor in the air relative to how much it can hold. Then it's more difficult to sweat because the water is being deposited on your skin a little bit more slowly than it's being evaporated. So it's harder to get rid of water vapor. And in a very humid environment, if you've ever been down south, like Louisiana in the summer, you know that the heat can be oppressive because of the humidity. Everything feels damp because even though it's not raining, you can feel very damp because of that relative humidity. So relative humidity is how much water vapor is in the air compared to the maximum amount it can hold. It doesn't mean 100% relative humidity does not mean we're underwater. It just means that the air is saturated, that it cannot take any more water vapor. So that's a saturation, a relative humidity of 100%. Well, what happens, get out of the way so you can see, what happens when you hit saturation? Well, when you hit saturation, the water starts to condense out of the air. Well, what does that look like? Well, dew or fog, right? Or rain. These are things that can occur when the relative humidity gets to 100%. Now, the warmer the air is, the more moisture it can hold. So when we get out to like the deserts of New Mexico and Arizona, there's very little water vapor in that air anyway, because most of it, as it comes in from the west, the air gets shoved up the mountains, it's cooled, it snows, and as that air comes back down, most of the water vapor has left the air. It's condensed as snow earlier on. And the higher temperature of their summers means it's a very dry heat. So you can walk around comfortably in 90 and 100 degree weather, shorts and a t-shirt in Arizona, and not really worry about it because your body is producing sweat, which is very quickly evaporating. So evaporation, sweating, is a very good way of getting rid of body heat in Arizona, New Mexico. You just have to make sure you stay hydrated so you have water to evaporate. You have sweat to use. Here in Wisconsin or in the southern states, right, swampy, warm states during the summer, evaporation does not work well as a means of getting rid of heat. So a 90 or 100 degree day can feel oppressively hot. The dew point is the temperature at which saturation occurs. And you've probably seen that if you've ever watched a weather broadcast, right? Oh, tonight's going to get 60, the dew point's 58. What does that mean? Well, as temperature drops, the amount of water vapor that can be held in the atmosphere also drops. And during the day, during a warm day, say 80 or 90 degree day, maybe the relative humidity is 80%. If the humidity doesn't change, in other words, I shouldn't say that, if the amount of water vapor doesn't change in the atmosphere and the temperature drops, the maximum amount of water vapor the atmosphere can hold drops as well. Eventually, the maximum amount of water vapor, so this is the amount of water vapor that's in the air, this is the maximum amount. As the temperature drops, the amount falls until they balance. Once they hit, you reach the dew point where saturation occurs, water has to leave the atmosphere. It leaves it in the form of fog. So some mornings, especially spring or fall mornings, where the temperature drops pretty dramatically in the evening from the summer days, you can get fog develop. You can get dew on leaves and so on. So you have what's called the dew point. And then of course, as the temperature continues to drop, the maximum amount of water vapor you can hold at saturation can't be less than the amount of water the atmosphere is actually holding. So this drops down, drops down, drops down. The maximum amount can hold drops down until it hits the amount it's actually holding, and then they go down together. And they stay at 100% until enough water leaves the atmosphere, the temperature warms up again, and then maybe the amount of water vapor in the atmosphere can change slightly. So that's dew point. So when the temperature hits the dew point, the atmosphere becomes saturated with water vapor. It has to come out at some point. It comes out as fog, dew, rain, and so on. Now, your book finishes by talking about boiling, and I'll let your book explain the process of boiling. Boiling is just you increase the temperature to the point where at 1 atmosphere of pressure, there's an unlimited amount of water vapor that the atmosphere can hold. So you just basically turn all of that water into vapor. Boiling, if you think about it, is actually a cooling process. It's not a heating process, right? It's the fluid trying to maintain a lower temperature. So when you heat something up on the stove, like a pot of water, right? A pot of water might start off at room temperature, say 70 degrees Fahrenheit. But as you add heat, that temperature of the water increases, 80, 90, 100, and so on, until it hits 212 degrees Fahrenheit or 100 degrees Celsius. Then the water doesn't increase in temperature anymore. Instead, you get a phase change. The water becomes vapor. The liquid becomes a vapor, but the water maintains its temperature. So it's actually the water attempting to stay cool, to stay 100 degrees Celsius and not heat up further. So boiling is indeed actually a cooling process, not really a warming process. And that's true for any type of boiling when you look at that phase diagram we showed earlier.